Hello and welcome back to the third video on the channel. Today we're going to be taking a look at the difference between transverse and longitudinal waves, or the differences in their properties. So transverse waves, in terms of their vibration, the vibration of the particle, have a direction of being perpendicular to the direction of energy propagation. Longitudinal waves are parallel. Now, transverse waves often feature crests and troughs. They look something like this, whereas the longitudinal wave composes of compressions and rarefactions. So if I try to draw something like this, we'll have a super compressed area of lines, and here it'll be more spread out, and here we'll have more stuff. So there are some other differences in the medium that they travel through as well. So transverse waves are limited to basically traveling through solids and the surfaces of fluids. Yep, it's like the ripple tank is an example of it, but they cannot travel in a fluid itself, whereas longitudinal waves can travel in all the states. So energy transfer is the same as the, let's say, the vibration of the particle here. So both of these are perpendicular to each other, whereas these are also the same because they're parallel. Examples of transverse waves include light and electromagnetic waves. Now, longitudinal waves, examples of them are sound waves and P waves. Now, we're going to go over the Doppler effect. The Doppler effect is defined as the change in frequency of a wave, right? When the source moves relative to a stationary observer. Now, if we go here, we can kind of find out that there's a stationary source, right? It's got quite an even distribution between each wave front. Whereas if we go to B, the source is moving. So whatever is in front of the source will often hear a much higher frequency, and whatever is behind the source will have a much lower frequency. So the conceptual understanding is that the wave fronts, as I have said, they have a much higher frequency. The source moving away means that there's a lower observed frequency. Now, I figure that most of you can determine the correlation between frequency and wavelength. Like, the higher an observed frequency, the shorter the wavelength, and the lower an observed frequency, the longer the wavelength. Since the speed of wave is determined by the medium, and the medium on Earth is sound, we can determine that it remains constant. There's a formula for this. It's called the Doppler effect formula. I don't actually know the name for it other than this Doppler effect formula. So it depends on what the question is telling you, but as a rule of thumb, the speed of sound is 343 meters per second, -1. For V. So if you're ever given a question, you may have to use this formula. So the FO is the observed frequency. It's equal to the source frequency times the speed of the sound in the medium. So the medium could be anything, but on Earth it's just 343 meters per second. And this is also the speed of sound in the medium again. But this is where it gets interesting. So depending on whether the source is moving towards you or away from you, the you may have to use plus or minus. So if the source is moving towards you, it's going to be minus. And if the source is moving away from you, it's going to be plus. Now, the next thing that we have to go over is the nature and the speed of electromagnetic waves. Now, EM waves are made up of two transverse waves. Okay, we've got the E, the B. Now, EM waves, they don't require a medium. That just means that they can go through almost anything, even vacuum. So, EM waves are distinct from your transverse waves. Well, they are a form of transverse waves, but they have magnetic fields at right angles to the direction of travel. So what that means is, if you look closely, there are two transverse waves that form the EM wave, and they're perpendicular to each other. See? Ooh. That means, oh wait, I shouldn't get into polarization just yet, but all electromagnetic waves travel at 3 times 10 to the 8 meters per second. You can determine the speed, the frequency, the wavelength, whatever they're asking for. I doubt it would ever be speed, but it might be one of these two, by substituting the value of 3 times 10 to the power of 8 into V, and then rearranging for whether they ask for your frequency or the wavelength. Now, the EM spectrum is a complete range of all EM waves. Despite all EM waves traveling at the same speed, they kind of have different frequencies / wavelengths. So, if you notice over here, radio waves are the farthest away, and they have quite honestly the longest wavelength. And the gamma rays have the shortest wavelength, meaning that they also have the highest frequency. So radio waves have lower frequencies is the correct word. So how I like to remember this is, I use the, what is it? Is it called an acronym? I forgot. I use the red Martians invade Venus using X-ray guns. Okay? We will know that the radio waves are always the much lower frequency, and as you approach gamma, it will have a much higher frequency. Now, we need to remember that there are specific uses for each of these. So radio waves are typically used for broadcasting. You've got your microwaves are used in, most obviously, your microwave and radar technology. You can use infrared to infrared radiation for thermal imaging. The visible light is most commonly found in human vision. And UV light can be used for fluorescent lamps and sterilization. The X-rays are used for medical imaging. Gamma is used for cancer treatment. So, visible light has a different spectrum as well. Humans can only view visible light within, I think, 700 to 400 nanometers. So, how I like to remember it is, I remember the visible light, again, is red being closer to radio, has obviously the much lower frequency. So I remember it as Richard of York gave battle in vain. Okay, stands for red, orange, yellow, green, battle, indigo, violet. That is pretty much all. The light travels at, again, 3 times 10 to the 8 meters per second. The next thing is, it's a continuation of EM waves. I should have done them together, honestly, but it's too late for that now. Polarization is a property that is exclusive to transverse waves. It's the phenomenon in which oscillations of transverse waves can be restricted to a particular plane. So what I mean by that is, if we see these waves, right, and pretend this is a nice little polarizer only allowing direction in this way, we would not get this wave coming through. We would only get the wave on the top coming through. That is because they have, basically, EM waves have directions perpendicular to the propagation, and they can be oriented so that it blocks out one entire oscillation, or a specific oscillation, and display only one. Malice's law describes how, we can, the intensity of the polarized EM wave can change after passing through every individual polarizer. So the transmitted intensity is usually related to this angle. It's the angle between the light polarization direction and the transmission axis. So the transmission axis is this one, and it's gonna have to deal with the angle created by this analyzer. So it's the combination of this slit and this slit forming to create the theta value. So Malice's law is given as the transmitted intensity is equal to the initial intensity times cos squared, the angle between the plane of polarization and the transmission axis of the analyzer. So let's say that we have unpolarized light coming through, right? Goes through the polarizer. It's restricted to a single axis. So it's only got this, and this specific axis coming through. So every time something goes through a polarizer, its value is halved. I don't question why we do it, we just do it. Probably because of the rule that states that every time the intensity passes through a medium, the intensity decreases. So if, let's say, the theta value did not align with the filter, it's not aligned, let me repeat that, then nothing will go through. If it's fully aligned, it will go through 100%. But let's say that if we shifted, let's say this, right? This would be shifted to this direction. We would get nothing because there's no oscillation or wave just going in the horizontal direction. So again, we just need to know that every time the polarizer goes through, the unpolarized light goes through a polarizer, its value gets halved, right? And it's only after that we use the halved value of the unpolarized light to substitute it into Malice's law. And that is the end of the waves topic for 9702 CAIE. I will make a past paper video soon.